Welcome to our time and space complexity cheat sheet. This handy guide helps you quickly understand the efficiency of algorithms in terms of both time, how long they take, and space, the amount of memory they use. Time complexity measures how an algorithm's execution time grows relative to input size, like a simple for loop that runs n times. Space complexity looks at the memory used, such as a recursive function creating multiple instances of itself, using up more space. We'll cover basic notations like O, n, omega, n, and theta, n, for different growth rates. By mastering these concepts, you'll be well equipped to choose the most efficient algorithms for your projects. Welcome to our tutorial on time and space complexity. First, we'll introduce the concepts of time and space complexity. Then, we'll dive into Big O notation, explaining how it helps us measure efficiency. Next up, we'll cover some common time complexities you should be aware of. We'll provide examples to show you the difference between efficient and inefficient code. To test your understanding, we'll have a quiz on identifying common mistakes in complexity analysis. Finally, I'll share practical examples for optimizing your code. Let's get started. Welcome to our tutorial on what is time complexity. Time complexity measures how the running time of an algorithm scales as its input size grows. Imagine you have a recipe that takes only 1 minute to prepare. No matter how many ingredients you add, that's O1. On the other hand, if doubling the number of ingredients doubles your prep time, it's O(n). Logarithmic time, like checking a phone book by pages, is O log n. And quadratic time, where operations increase exponentially with input size, such as in nested loops, is O(n squared). Understanding these notations helps us pick the most efficient algorithm for our tasks. So, let's dive deeper into optimizing your code efficiency. Welcome back to our journey through time and space complexity. Today, we dive into the concept of space complexity. Simply put, space complexity measures how much memory your algorithm needs as it processes larger inputs. This includes both the space used by the input data itself and any additional space for variables or temporary storage, what we call auxiliary space. For example, if you're sorting a list of 10 items, that list takes up some space. But so might a variable storing intermediate values during processing. We often describe these using notations like O1 for constant space, On for linear growth with input size, and O log n for logarithmic growth. The goal is to use as little memory as possible, making your algorithms more efficient and responsive. Welcome to our example of linear time complexity, which we represent as O(n). In this code snippet, we have a function called linear_time that takes an array ARR as input. Let's break it down. Inside the function, we initialize a variable count to 0. Then, in a loop, we iterate through each element of the array, incrementing our count by 1 for every item. This means if you have n elements in your array, this process will run exactly n times. The time complexity is directly proportional to the size of the input, making it linear. Importantly, notice that this function only uses a single variable count, so its space complexity is O1. This is part of our comprehensive cheat sheet on time and space complexities, helping you understand how algorithms perform with different inputs. Welcome back to our Tech Fundamentals series. Today, we're diving into the output of linear time complexity code. Imagine you have an array with numbers 1, 2, 3, 4, 5. Our function iterates through each element exactly once, no more, no less. This means if your input size doubles, so does the processing time, keeping it directly proportional. The time complexity here is O(n), where n represents the number of elements in the array. But here's the cool part. This function only uses a fixed amount of memory, making its space complexity O1. Let's see how it plays out in code. And then we print the result. Ready to try it yourself? Dive into your editor and experiment with different arrays. Welcome to our coding efficiency tutorial. Today, we're diving into finding the maximum value in an array. Let's start with an inefficient approach. Imagine you have a list of temperatures, and you want to find the highest one. An inefficient way would be to loop through each temperature, comparing it with what you think is currently the highest. This can get messy if your dataset grows. Now, let's look at an efficient method. Instead of constantly comparing every single element, we simply store our current maximum in a single variable and update it whenever we find something higher. It's cleaner, faster, and works great even with large datasets. So next time you're coding, remember, keep your code lean and mean. By the way, this is just one example of how understanding time and space complexity can help you write more efficient programs. Stay tuned for our cheat sheet on these concepts. Alright, let's dive into this quiz question. You're looking at the function which is designed to find the maximum value in an array. The function initializes a variable with the first element of the array and then iterates through each number in the array. If it finds a number greater than the current, it updates. Now, here's the question. What is the time complexity of this function? Take a moment to think about it. The answer is O(n). Why? Because the function goes through each element in the array exactly once. No matter how big or small the array is, it will always take one pass through the entire list. This makes its time complexity linear with respect to the size of the input array. Let's move on to our next topic. Let's dive into an example of quadratic time complexity, denoted as O(n squared). Here's the code. We have a function called that takes an array as input. Inside this function, we initialize a counter variable to 0. The core of our operation is two nested loops, one iterating through each element in, and another inner loop also iterating through every single element in. This means for each element in the outer loop, the inner loop runs n times. As such, if you have an array with n elements, this function will make n*n operations, which is why it's quadratic time complexity. In simpler terms, if your input size doubles, the number of operations quadruples. Let's break down a small example. For an array of 3 elements, we would perform 9 operations, 3 by 3. And for 4 elements, that's 16 operations, 4 by 4. That's how O(n squared complexity can quickly become inefficient as the input size grows. Alright, let's dive into this slide. We've got a function that uses nested loops, making its time complexity O(n squared). This means the execution time will grow exponentially with the size of the input. For example, if you double the input size, the runtime could quadruple. On the bright side, our space complexity is a constant O(1), meaning it doesn't depend on the input size. Here's how it looks in code. This function takes an array as input and processes every element with each other. Remember, when dealing with nested loops like this, always be mindful of performance. Let's move on to the next slide to see how we can optimize this code for better efficiency. Welcome to our optimization techniques tutorial. Today, we're diving into the wrong versus right way to optimize code. Let's start with the wrong approach. Imagine you have a project where every tiny piece of logic is stuffed into its own small function, too many, in fact. This can lead to slower execution because your program has to switch contexts too much. But here's the thing. It's not just about speed. It also makes your code harder to maintain and debug. Now, let's look at the right way. Instead of over-fragmenting, combine similar tasks into fewer, more efficient functions. This approach reduces redundancy, enhances readability, and ultimately leads to better performance. For example, if you find yourself doing a lot of repetitive calculations or operations, bundle them together in one function. That's your key takeaway. Less is more when it comes to efficiency. Let's dive into an example of how we can optimize our code for efficiency. Before optimization, our function processes each item twice, leading to redundant operations and potentially slower performance. We can see this in the original code where both loops iterate over the same data. But here's what happens after optimization. By combining the logic inside a single loop, we eliminate unnecessary iterations and improve efficiency. Our optimized function now processes all items once with combined logic, making it faster and more resource-friendly. This is a great example of how simple adjustments can lead to significant performance improvements in your code. Alright folks, let's dive into this quiz. We have 2 approaches to consider. Approach suggests using multiple small functions for each task. Imagine you're baking a cake. Each step, like mixing the batter or adding frosting, would be its own function. On the other hand, Approach B combines similar tasks into fewer, larger functions. It's like if you had a recipe that combined all your cake steps in one big process. So, which is better? Well, it depends on the situation. Smaller functions can make code more modular and easier to debug, but combining similar tasks might reduce redundancy and improve performance. Which approach do you think would be more efficient for a complex application with lots of repetitive actions? Let's decide together in the comments. Great job, everyone. Let's wrap up today with some key takeaways. First, mastering time and space complexity is crucial for writing efficient algorithms. Think of it like packing a suitcase. Every item you put in should have its purpose. Big O notation helps us describe how an algorithm performs as the input size grows, just like knowing if your luggage will fit on a small or large airplane. Next, look for ways to combine similar tasks into fewer functions. It's like merging multiple trips into one to save time and energy. Lastly, always consider the input size when choosing between different approaches. What works well with 10 items might not be as efficient with 100,000. So, remember these tips and apply them wisely in your coding journey.